Here we are finishing up our Chapter 3 Quest review video, and we are going to graph this rational function. So to graph a rational function, let's remember what we learned in class in a previous video, that first of all, this constant that is added on to the function is where we are going to get our horizontal asymptote. So we have a horizontal asymptote at y equals -3. So down to 3. Here's our horizontal asymptote. Then our vertical asymptote is found by whatever our restricted value is from our domain. So our domain is restricted and it cannot be +1. So we have a vertical asymptote at x equals 1. So x equals 1. Here is our vertical asymptote. Now essentially what these two asymptotes have done is they've created a new origin for us to use as our axis. So basically first quadrant, second quadrant, third quadrant, fourth quadrant. Now here's what I know based on what we've done so far with functions and graphing. This is the a value on the top. So our a value is -2. So instead of our branches of our asymptotic graph being in the upper right and lower left, it's going to be flipped. So we should have graph here and graph there based on that a value being -2. Now remember, I'm not going for precision here, but we get the asymptotes in the right spot then, and we know where the branches are going to be, then the whole thing should make sense. So let's go to an XY chart and let's plot a few points. So let's plug in 0. Easiest thing to plug in always. So -2 over -1, that's 2. 2 minus 3 is -1. Over 0, down -1. So there we go. It's what we're expecting. It's going to be in these two quadrants. Let's put in +1. We put in +1, we're expecting it right over here, and it should be basically symmetrical with that first point. So -2 over -2 is +1. 1 minus 3 is -2. So, excuse me, not 1, but 2. My bad. 2 minus 2. 2 minus 1, 1. -2. So I do have it wrong. 2 over 1 is -2 minus 3, -5. There we go, which makes more sense. 1, 2, 3, 4, 5. There you go, symmetric with respect to the other point. That's looking better. Let's do 3. So that is -2 over 2. That's -1. -1 minus 3 is -4 over 3, down 4. So we've got this branch. And if there's a point there, which is down 2 over 1, up 2, back 1, on that particular asymptote, because these branches are symmetric with respect to this particular origin of these two axes. So there you go. That is a rational function. What's our domain here? Just thought I'd give a plug for the domain. It's everything but 1. So -infinity to 1, union 1 to infinity. Our range is also restricted in this particular graph. It's everything but -3. So -infinity to -3, union -3 to infinity. There we go. That's a rational function. 2 more quick problems here. So first of all, we've got a word problem, a variation problem. The volume of a pyramid varies jointly as its height and the area of its base. A pyramid with a height of 15 feet and a base with an area of 35 square feet has a volume of 175 cubic feet. Find the volume of a pyramid with a height of 20 feet and a base with an area of 120 square feet. So let's go back, look at that first sentence, and let's translate it to an equation. The volume varies jointly as its height and the area of its base. So volume varies jointly. Remember, joint variation is all multiplication. So varies jointly as its height and the area of its base. Normally we say that that is big B when we're talking about the area of its base. So this is your joint variation. A pyramid with a height, okay, so now we're getting more information, so let's highlight that. We've got a height of 15 feet and an area of the base of 35 square feet is yielding a volume of 175 feet. So let's take those givens and let's plug them in to our variation statement. So volume is 175. The constant of variation, K, is unknown. I want you to solve for that first. The height is 15. The area of the base is 35. So what is our constant of variation here? So if we calculate this, so first of all, we just need to divide by 15 times 35, divide by 15 times 35. So 175 divided by 15 times 35 gives us 1/3. We have a constant of variation of 1/3. So K equals 1/3. Rewrite our variation statement. Volume equals 1/3 of the height times the area of the base. So now, let's go to the rest of the problem. Find the volume of a pyramid with a height of 20 feet and an area of the base of 120. So using our freshly found constant of variation, we're going to solve for a whole new volume. Volume equals 1/3 of the height, which is 20, times the area of the base, which is 120. The 3 will cancel with the 120 40 times, and we find 20 times 40, that is 800. We're talking about feet, so that is 800 cubic feet for the volume. So this is the type of work that I'm looking for when I ask you to solve a variation problem. Write the statement of variation, find the constant of variation, and then answer the question. 3 parts there. Last question, if you are given a variation and I ask you to describe it, that means I want you to use words. So let's pick this thing apart first. So first of all, there's our K value. And it looks to me that since we are dividing, we've got 2 different types of variations going on here. First of all, we're multiplying by x squared and we're dividing by the square root of x. So this is a combined variation. So if I had to rewrite this in terms of words, I would say y varies directly with x squared, and inversely or indirectly, same word, as the square root of z. The constant of variation is 0.175. That is how I would describe this particular algebraic variation equation. And that is everything you need to know for our quest that will be coming up as soon as we come back to school.